Welcome back to Statistical Methods. This is week 6, lecture 2. And today we'll be covering decision errors, power, and effect sizes. But first, we need to learn how to calculate something called a confidence interval. Now, confidence intervals provide a kind of margin of error for a calculated statistic. For example, a sample mean, an effect size, or a z-score. So in other words, whether the statistic is fairly precise or likely to be close to the true mean or effect size or z-score in the population. It's basically a rough estimate of whether our estimate of a particular statistic is corresponding with the actual statistic at the population level. Confidence intervals take the form of ranges of values, for example, 3.0 to 4.5. whose upper and lower bounds are known as confidence limits. Now here's the calculation for a confidence interval. So a confidence interval equals the mean plus the critical z-value multiplied by the standard error of the mean. Now note that this is plus or minus, or in this case, plus and minus. Right, so the mean is simply the sample mean. The critical z-value is the z-score which leaves 100 minus the confidence interval divided by 2% of means in the tails of the distribution. So this is a little confusing. But for example, if we want to find a 95% confidence interval, we need to find the z-score that isolates 2.5% or p equals 0.025% of scores in each tail of the distribution. So we already know this z-value, which is 1.96. So for z critical here, for a 95% confidence interval, we're going to use z equals 1.96. Now, if we wanted a 99% confidence interval, we would find the z-score that isolates 0.05%, or p equals 0.005 percent of scores in each tail of the distribution. So that would be an even larger z-value. And sigma m is the standard error of the mean, which we talked about in the last lecture. So let's say I calculate a sample mean of 12, and my standard error based on my known standard deviation for the population is 3. Now let's calculate the 95% confidence interval. All right, so my formula is the mean plus or minus the critical z times the standard error. Now we have a mean of 12, so we'll sub that in for m, plus or minus the critical z value times 3, which is our standard error. So what is that critical z-score? Now the z-score that isolates 2.5% of the distribution in the tail is what we need here, because we're looking for a 95% confidence interval. Right, so that's 100 minus 95 divided by 2. Or in other words, 0.05 divided by 2, which is 0.2025. And the z-value that corresponds to 0.025 is 1.96. So again, we take our mean plus or minus 1.96 multiplied by 3, which is 12 plus or minus 5.88. So our 95% confidence interval here is 6.12 to 17.88. So again, we got that from adding 5.88 to 12 or subtracting 5.88 to 12. Now let's say I calculate a sample mean of 12 and my standard error based on my known standard deviation from the population is 3. And now I want to calculate a 99% confidence interval. So everything else is the same, except this time I need to find a z-score that isolates 0.5% of the distribution in the tail, leaving 99% in the middle. And as I said earlier, this is a larger z-value, 2.58. We get that from our Shiny app or the standard normal table. And this time we add 12 plus or minus 2.58 times 3, or 12 plus or minus 7.74 And our 99% confidence interval is 4.26 all the way to 19.74. Now, how do we interpret a confidence interval? Well, the correct interpretation is, for a 95% confidence interval, if we collected 100 samples and calculated confidence intervals for all of them, 95% of them, or rather 95 of them, would be expected to overlap the true population mean, mu, or whatever parameter is being estimated, whether it be a mean or a standard deviation or an effect size. Now, another way to interpret it is the wider the confidence interval, the less confidence we have that our sample mean precisely estimates the population mean. So I won't ask detailed quiz questions on that. They might come up a little bit in the homeworks, but those are, again, graded for completion. But you'll want to know the conceptual basis here. And particularly this page is what you should focus on, how to interpret a confidence interval. So now I'll talk about decision errors, statistical power, and effect sizes, which is the heart of this lecture. So as we've seen so far, null hypothesis significance testing procedures will lead a researcher to one of two conclusions. We either reject the null, which means that our study supported our hypothesis, or we fail to reject the null, which means that our study is inconclusive. Now, because null hypothesis significance testing is based on probabilistic thinking, it's possible to reach the wrong conclusion about the existence of an effect, despite using the correct statistical procedures. Now, these wrong conclusions are known as decision errors, and they come in two varieties. The first one is a type 1 error, or a false positive. So a type 1 error occurs when we falsely reject the null hypothesis. In other words, we find a p less than the significance level and conclude that the study supports the research hypothesis, when in reality, the null hypothesis, the hypothesis that there is no effect, is true. So, for example, a pharmaceutical researcher concludes that a drug works based on a p-value of less than 0.05, even though the drug actually has no effect at the population level. So in other words, this researcher found an extreme result simply due to random chance. How frequently would we expect type 1 errors to occur? So if we're using a significance level of 0.05, about 1 in 20 times. That is, finding a result so extreme that would happen only 5% of the time when the null is true. Extreme results will sometimes happen by chance, as opposed to because of some true effect of the independent variable. Thus, the significance level is equivalent to the probability of making a type 1 error. This probability is known as alpha. So when researchers set that standard of evidence that we've been calling the significance level, or we're looking for a p-value less than 0.05, they're also setting alpha. So you could think of type 1 errors as analogous to the boy who cried wolf parable. So crying wolf when that wolf isn't there is somewhat like concluding that there is an effect present when in actuality there is no true effect. This is a good mnemonic for remembering. Type 1 error means false positive. We're claiming something is there even when in actuality it isn't. Now, a type 2 error is the exact opposite. It occurs when there is a true effect in the population level, but we fail to find it in our experiment. In other words, we failed to reject the null hypothesis, even though the research hypothesis that there is a relationship between variables is true. So for example, a pharmaceutical researcher tests a new drug and finds p is greater than 0.05 and fails to reject the null that the drug has no effect. But in actuality, the drug does work, and the researcher simply didn't find an extreme enough result large enough to reject the null. Now, the probability of making a type 2 error is known as beta. Unlike alpha, which is simply set by the experimenter in advance, beta relies on several things. For one, it relies on the effect size. So the larger the effect, the harder it is to miss it. This is fairly intuitive. But it also relies upon sample size. The larger the sample size, the easier it is to reject the null hypothesis, or the harder it is to miss a true effect. And it also relies upon alpha, which is set by the researcher. So the higher, more lenient the alpha, or in other words, setting a p-value as your cutoff larger than 0.05, the easier it is to reject the null hypothesis. Thus, the harder it is to miss a true effect. So an easy rule of thumb here is as effect size, sample size, and or alpha increase, beta decreases. And beta, again, is the probability of making a type 2 error, or a false negative. Now, here is a chart that plays out what these errors look like. So let's say, in actuality, our null hypothesis is true, but our research hypothesis is somehow supported by our data, and we reject the null hypothesis because we found a p-value less than 0.05. We've made a type 1 error. That's a false positive. And the probability of obtaining that false positive is expressed as alpha. Now let's say our null hypothesis is true, there is no effect at the population level, and our study is inconclusive, and we do not reject the null hypothesis. That's a correct decision. So there is no effect, and our results are inconclusive. That's what we want to happen when there is no effect at the population level. Now let's say our research hypothesis is true, so there is an actual effect at the population level. And our research hypothesis is supported by our data. And we wind up rejecting the null hypothesis because our p-value is less than 0.05. Well, we've made a correct decision. There is an effect, and our data were able to find that effect. Now, finally, if our research hypothesis is true at the population level and in reality, but our study is inconclusive, and we fail to reject that null hypothesis because our p-value is greater than 0.05, we've made a type 2 error, a false negative. And the probability of that false negative can be expressed as beta. Now, the fundamental problem here is that there isn't any way to know when a researcher has committed one of these errors. So this would require knowing the true population parameters, which we usually don't. All we know about them is the data we have from the experiment. So all we have are estimates. Thus, researchers must do what they can to minimize the chances of committing both of these errors, both these alpha and beta errors. And how do they do that? Well, to minimize type 1 error, we need to set a low, conservative, or stringent alpha. Remember, alpha is the significance level, which the experimenters set themselves. So setting a low significance level means that you'll require a more extreme result in order to reject the null hypothesis. And by more extreme, I mean less likely if the null is true. Now, how do we minimize type 2 error? Well, we need to remember that beta varies as a function of three things: effect size, which is not under the experimenter control; alpha, which is under experimenter control, but raising this means that we're also raising type 1 error probability; and sample size, which is absolutely under our control. So the best way to minimize beta without sacrificing alpha is to get the biggest sample you can. That's the big takeaway from this section. So the best experiments will use a reasonably conservative significance level, so low but not so low that it would be impossible to ever reject the null hypothesis, and collect a large sample to minimize the chances of committing a type 2 error or missing an effect that is actually there. Now, type 2 error also relates to another important concept in statistics: power. What is power? Well, power is 1 minus beta. In other words, the probability of not committing a type 2 error. Stated more clearly, it's the probability of your experiment to detect a true effect, or to reject the null hypothesis when that null hypothesis is false. So it is in an experimenter's interest to maximize statistical power. Well, how do we do this? The same way as minimizing beta. We collect larger samples. Researchers will often conduct what is called a power analysis before they conduct their experiment. So an a priori or from before power analysis requires as input the significance level, or alpha, which is usually 0.05, the effect size you want to be able to detect, and the desired power. And as output, you will get the required sample size to detect an effect of the desired size with a particular level of power given your significance level, which is usually p equals 0.05 or p is less than 0.05. Now, there is a free software for conducting power analysis for different kinds of statistical tests, and it's called G-Power, and you can find it at this link if you're interested. Now, here's what G-Power looks like. So let's say you're looking for a difference between two independent means, so two different groups. And you have a two-tailed test because your hypothesis is non-directional. And you expect to find an effect size of 0.5, so that's a half of a standard deviation mean difference between these two groups. And you set alpha at 0.05, which most researchers do. Again, that's your p-value cutoff. And you're looking for 95% power. So a 95% chance of your experiment rejecting a null hypothesis when that null hypothesis is false. And this here is just specifying that you have equal sample size in each of your groups. So if you hit calculate, you'll learn that you need a sample size of 210 participants in order to detect an effect of Cohen's d equals 0.5, which is again a half standard deviation, 95% of the time. So that's generally how you use G-Power. I use this all of the time for my own experiments and research. Now, knowing the power of a study is useful for interpreting its results. If a researcher fails to reject the null by finding a p-value greater than 0.05, but the study is underpowered, it becomes difficult to interpret this conclusion. So is there really no evidence for an effect, or was the sample size just too small to detect the effect that is actually there? Now, because of this, academic journals are now beginning to put stricter requirements on power and sample size justification. Now, this isn't only in social science, this is across all sciences, including physical sciences. So what is an acceptable level of power for a psychological study or a sociological study? Well, previously 80% power was the standard. So that is a 0.8 probability of detecting an effect of the specified magnitude if that effect is actually there. However, there are concerns about following this old recommendation. Now, people wonder whether an expectation of 80% power is sufficient. And people also wonder whether most of the published studies are actually even achieving this minimum cutoff, particularly those that aren't justifying their sample size with a power analysis, which is most published studies in the field. So a paper was done by a researcher named Ioannidis in 2017 that found that median power to detect small, medium, and large effects was 0.12, 0.44, and 0.73 across different fields, reflecting no improvement on power across the last half century. And this is because sample sizes were too small in the published literature. Now, assuming a realistic range of prior probabilities for null hypotheses, the false report rate, report probability is likely to exceed 50% for the whole literature. So this means that because sample sizes are so small in many of the published studies across different scientific fields, there's a good chance that 50% of the results published in academic journals aren't true. Now, there is a Shiny app for visualizing how beta and power are affected by alpha, the effect size, so the difference between the null hypothesis the distribution and the alternative hypothesis distribution means, and the standard error of the mean. Now, in this app, the red shaded region gives you alpha, so the probability of finding a result from the null distribution that would lead you to reject the null. The blue shaded region gives you beta, so the probability of finding a result from that alternative distribution that would lead you to fail to reject the null hypothesis. So just try playing around with these to give you a good sense of how power fluctuates as a result of sample size, alpha, and effect size. And just as a note, this app only gives you beta, so you'll need to do the 1 minus beta calculation yourself to find power. But it's a cool way to visualize power and type 1 and type 2 error. You won't be tested on this. It's more for fun. So we've already discussed effect size a few times in this class, and we've now seen its importance in type 2 error and power considerations. Now, the larger effect, the easier it will be to find it. The greater the power, the lower the type 2 error probability. Now, I've mentioned before that one of the main reasons we care about effect size is gauging the practical magnitude of effect, since p-values take both effect size and sample size into account. But I haven't yet demonstrated how and why this is the case. Though this is sorry, I got distracted there by some construction going on in my building. So what I was saying is that I haven't yet demonstrated how or why this is the case, because this required first knowing about sampling distributions of means and standard error of the mean. So let's recall the central limit theorem. What we learned from this is that as sample size increases, standard error of the mean decreases. In other words, our sampling distribution of the mean gets narrower. Here's a visualization of this. And the practical consequence of this for null hypothesis significance testing is that the same sample mean will translate to a more extreme z-score with a lower p-value in a narrower sampling distribution. Thus, even when we hold effect size constant, larger samples will drive p-values down. This can be easily seen by looking at the formula for a z-score based on a sample mean we learned last time. So again, z equals the mean of our sample minus the mean of the sampling distribution of means divided by the standard error of the mean. Now, a larger n drives standard error of the mean down, because this is our standard deviation divided by radical n. So larger sample size, smaller standard error of the mean. And as standard error of the mean gets smaller, our z-score gets larger, even if this numerator stays the same. So if a researcher knows that the general population of babies' walking ages has a mean of 14 and a standard deviation of 3, now imagine two hypothetical experiments. In study 1, the researcher gives a vitamin to n equals 5 babies and calculates their mean walking age to be roughly 12 months. Now in study 2, the researcher gives the vitamin to n equals 100 babies and calculates their mean walking age to be n equals 12 months. So the same, right? So you notice here that these effect sizes are exactly the same. What about the z and p values? Now, calculating the z for each of these, 12, our mean, minus the population mean of 14, divided by 3, our standard deviation, divided by radical sample size, gives us negative 1.49 for study 1, which had a sample size of 5, and for study 2, negative 6.67, which had a sample size of 100. Now note that the difference here is only in n, the sample size. Now what about the p-values? For study 1, our p-value is 0.068, so we can't reject the null. So our study is inconclusive, but the p-value for study 2 is 0.000036, very small, and we can absolutely reject the null and find support for a hypothesis. So a difference in sample size, but not effect size, produced the two very different conclusions. Now, this isn't entirely illogical. Remember that bigger sample sizes give us more precise estimates of population parameters that we're interested in. Thus, we can trust them more than smaller samples. And p-values incorporate this greater level of confidence. However, sometimes a reader will want to get an absolute idea of the magnitude of the effect in a way that is free from sample size, particularly important for understanding the practical magnitude of effects. Now, the textbook goes further into detail about the calculation of specific effect sizes, but I'll save this for later on in the semester. And I'll teach effect sizes along with the specific statistical tests that they're associated with. But just as a preview, t-tests use a Cohen's d effect size estimate. ANOVA correlation regression use r squared or eta squared. And the chi-square analysis uses phi. But I will get into this more as we cover these particular tests throughout the semester. And I believe that is all for this lecture. Thank you. Also, sorry about the construction in the background.